Hello. So far we have talked about compliant mechanisms and their mobility analysis, because the Grubler's formula that has been developed for rigid body mechanisms can also be used for compliant mechanisms, which is what we saw in the last lecture. Today we will contrast and compare this Grubler's formula that is used in rigid body mechanisms literature with what is used by structural people, that is, let us say civil engineers, who do not want the structures to move at all or move very little. They use something called Maxwell's rule, and with that also one can find the mobility or degrees of freedom. And there is another concept that we learned today called states of self stress. This comes from the stiff structure literature, and as we emphasize in this course, compliant mechanisms lie in between rigid body linkages and stiff structures. So, we have the luxury of using concepts from both fields and enrich compliant mechanisms field. So, let us look at the Grubler's formula and what its deficiencies are, and then consider Maxwell's rule and what its deficiencies are. Turns out both are actually equivalent. So, let us start with what we have already discussed, which is this degrees of freedom formula for compliant mechanisms, where we have modified it. Okay. The modifications, once again I will underline. First of all, this number of segments instead of just number of bodies, and the inclusion of elastic pairs. While this corresponds to kinematic pairs, this corresponds to kinematic pairs. Now we have elastic pairs, and then we have these fixed connections which are needed whenever an elastic segment is connected with another elastic segment, okay, or elastic segment is connected to a rigid segment. We have to have these fixed connections, and then we had this concept of segment compliance, which we had dealt with in the last lecture. And at this point you all are familiar with how to use this formula. We had done it for 2D also, which is shown here. It is just that freedom 6 becomes 3, that 6 again becomes 3 here in all of these places, and number of fixed connections when you have, again instead of 6 we have 3, because in planar case there are only 3 degrees of freedom, and this goes only from 1 to 3 as opposed to 1 to 6 over there. That is all the difference there is between 3D and 2D formulae. Now, let us consider this example, which again should be familiar to all of you, that if I say this is fixed frame and there are 2, 3, 4 and 5. So, n here or n seg, whichever we look at, we can call it n seg, even though there are no elastic segments here, that is 5, and then n k 1 joints, there are 6 of them here. So, degrees of freedom for this, there are no NK2 joints or elastic segments or elastic pairs here. So, we have 3 into 5 minus 1 minus 2 multiplied by 6, that gives us 12 here, 0. So, according to this formula, this is not supposed to move, but it does, because it has parallelograms. There is one parallelogram here, there is another parallelogram over there. Because of that, we can easily see that when I turn this, it happily moves with 1 degree of freedom. So, this formula here, it is not working, and that is not surprising, because we are only counting. In Grubler's formula, we are counting number of bodies, or in modified form number of segments, and the number of pairs, whether they are kinematic pairs or elastic pairs, and the elastic segments, and assigning the segment compliance, a number that we will learn to interpret with practice, right. So, we are only counting, we are not actually taking into account the exact geometry. Here these 5 bodies are arranged to form 2 parallelograms, and that is not reflected in the formula. If I were to take arbitrary quadrilaterals here like this, where I have this ternary link, and then here is where we have the fixed joints, then it will not be able to move. Then this formula is actually correct, but the special geometry that comes is what is making this formula not work. There are a number of other examples. Here what you see are two configurations of what is called a kaleidocycle mechanism, and this one has a degree of freedom. If you were to make with 6 tetrahedrons joined together with 6 revolute pairs. In fact, we have called it elastic pairs here because we have joined with these flexible tape, right. There are 3 joints there and the 3 joints are like this. They have a particular configuration here. Because of that, even though it is movable with 1 degree of freedom, in fact, what we have shown from here to here is actually turning it around, right. It just rotates about these axes in a very interesting way. It makes an interesting toy, but it actually has a name. It is called a Bricard linkage because of the special geometry it has. If you see over here in this figure, all the revolute joints, they are all hinges, they all meet at a point and they have a certain angle and certain symmetry to it. Again, that symmetry is not accounted for in our formula for degrees of freedom, and hence it predicts 0 degrees of freedom, whereas this has a single degree of freedom. There are many more examples, especially in the spatial linkages where the formula fails with great glory. It is not the formula's mistake, it is just that mechanism that we consider have special geometries, so special that we actually give the name of a person. Whenever we give name of a person to something, it is very profound. Here Bricard realized that if you configure them in this particular way, you get a degree of freedom that normally does not happen if you were to take 6 links, 6 bodies arbitrarily with 6 revolute joints. Okay. So, the formula fails. So, we look for alternatives. One of the alternatives, because compliant mechanisms can get enriched by taking concepts from rigid body linkages as well as stiff structures, we go to this what is known as Maxwell's rule. The same James Clerk Maxwell who gave us the equations of electromagnetism, he also had worked on structures a lot and optimization, structural optimization, mainly to build his instruments. He was such a great person, was able to contribute fundamentally to these fields as well. Here is what we see, a simple and elegant rule which is named after Maxwell, which again has a 2D version, planar version and a 3D version. It is a very simple formula, 2V minus 3 minus B equal to 0, where V is the number of vertices and B is the number of bars. So, here he is looking at only trusses. Trusses are very important elements of structures. We find lot of trusses around us. He was analyzing trusses and he found this interesting relationship which is called Maxwell's rule now, 2V minus 3 minus B equal to 0 in 2D, 3V minus 6 minus B equal to 0 in 3D. What he says is that if a truss satisfies this relationship in 2D or 3D, depending on whether it is a planar truss or a spatial truss, that such a truss will be just stiff, meaning that it has enough constraint so that it does not deform. It can deform by elastic deformation, that is a different thing. It will not be able to move, meaning that it is stiff. So, if we take let us say our first example of a triangle, 3 bars. So, here V equal to V is equal to 3 and B is also equal to 3. There are 3 bars, 1, 2, 3 and then 3 trusses, I can call it 1, 2 and 3. 3 vertices and 3 bars. So, if you see this formula, 2 times V, that gives 2 times 3 minus 3 minus number of bars 3, that is equal to 0. So, that means that a triangle is just stiff. We can feel that, if we take triangle made with 3 bars, it will not have any play, it is actually stiff, right. Now, let us take this example where the 2 triangles are connected together. For this one, let us write the Maxwell's rule. Let me choose a different color, so we do not mix it up. So, here vertices are 4 and number of bars is 5, 1, 2, 3 we have added 2 extra bars, let us call this 4 and 5, while this is 1, 2 and 3. If I write this formula, this is a planar truss. So, 2 times 4 minus 3 minus 3 minus 5, again it is equal to 0, meaning that this is also just stiff as Maxwell said. When you say just stiff, it also has another connotation that these trusses are statically determinate, meaning that the internal forces in the members of the truss can be determined purely from equations of static equilibrium. That is what we mean by static determinacy, that I am sure you would have heard in your mechanics of materials class when you discussed beams and trusses and so forth. Static determinacy. What it means is that from equations of static equilibrium alone, we can determine the internal forces in the truss. So, now let us take this one. Okay. So, let me erase this line a little bit and choose a different color. So, there is no confusion again. Okay. Now, how many vertices are there? 4, only 4 like the previous one, and how many bars are there? There are 6. Okay. Now, let us write the formula Maxwell's rule, 2 times 4 minus 3 minus 6. So, this one has minus 1 because this is 8 minus 3 5 minus 6 minus 1. So, this shows that we have a case where it does not satisfy the so called Maxwell's rule. In that case, this particular truss is not statically determinate, which we know, and it is not just stiff, it is more than being just stiff. We can see that from here to here, when I am adding this extra line, I am not actually stiffening the structure, I am over constraining it. In fact, if 6 bars are given which have arbitrary lengths, when you assemble, if they follow triangle inequality, you can always assemble, and same thing happens with 2 triangles if the bars that are given satisfy triangle inequality. But here after this, if I give the 6th bar to be put in here, if it is shorter than or longer than this distance, in order to assemble this one, either I have to stretch it or contract it. If it is shorter, I have to stretch it, if it is longer, I have to contract it and then assemble. When I do that, this particular structure will be in a state of stress. It will have some residual stress even before you apply any external forces. Okay. Such a thing is called a state of self stress. It comes from the way it is assembled and not because of external load acting on it, and that is what Maxwell was getting at. So, he said that whenever it is 0, then it is just stiff. If it is negative, then it has this state of self stress. So, in this case, if it is minus 1, it has one state of self stress. So, this is all interesting, but if you take an example such as this one, what I have shown here is basically a rectangle. So, here if I were to write it, number of vertices 4, number of bars only 4. Now, if I write the Maxwell's rule, 2 times 4 minus 3 minus 4 equal to, this is 8 minus 7, that is 1. So, this particular 1 actually gives degree of freedom. If you notice, this is nothing but our 4 bar linkage, 4 bar linkage. So, it actually gives a degree of freedom that this one has. So, Maxwell's rule can be applied instead of Grubler's formula because it gives you degrees of freedom, but it also gives you what we call state of self stress. Okay. So, let us look at that in a little bit more detail. Let us take this example now. So, here again if I say number of vertices is 6, number of bars 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 bars, and if I write this formula, 2 into 6 minus 3 minus 9 equal to 0. It is just stiff, that is obvious when we look at it because it is only triangles, triangles are just stiff, they do not have any over constraint. But now if I go for this, where I have taken this bar, okay, and put it like that. That is all. That is a change that we see over here. So, in terms of number of vertices, number of bars, whatever we have written holds for this one also. But then here it says 0. But we just discussed that this part of the structure has one state of self stress. Okay. So, this SOSS, what we mean is that it is state of self stress, or we can understand this as an over constraint. Just like a degree of freedom requires certain mobility, some movement to a truss or a linkage, both are actually equivalent if you view from the perspective of Maxwell's rule. Something that has over constraint, such as the one that we have encircled here, it has a state of self stress, that is, you have to stress it in order to assemble if you are given 6 arbitrary links. But then the top portion here is a 4 bar linkage. So, that has a degree of freedom, this has a set of self stress. So, according to the formula, this will have positive 1 degree of freedom, this has, according to, instead of 0 will have negative 1 as we saw. So, this particular portion from the formula gets minus 1, this other portion gets plus 1, both of them added give 0, which is what we see here. So, there is confusion when you apply Maxwell's rule, that sometimes even if it is 0, you do not know if some part has a degree of freedom, some part has this over constraint or state of self stress. Hence, the Maxwell's rule was modified by a professor at University of Cambridge called Christopher Calladine. What he did was, instead of 0, he put this. He said degrees of freedom minus state of self stress, or SOSS, states of self stress in plural. What it means is that so much over constraint is there, which is the opposite of degree of freedom. That is how we should understand. Okay. So, again number of vertices V, number of bars B, now we get DOF minus SOSS. The same thing applies to 3 dimensional trusses as well. When you have something like this, when it is 0, it actually means there is a plus 1 and a minus 1. Okay. One state of self stress, 1 degree of freedom. We have some examples. This is taken from an engineering mechanics book, which is a plain old truss. We have there are 5 vertices here, which you can count, and there are 7 bars. So, we see 1, 2, 3, 4, 5, 6. You may wonder where is the 7th one. The 7th one is here, okay, because it is connected, or the fixed frame that we have, right. That bar has to be connected to make this truss. By the way, Maxwell's rule does not consider the fact that one body is fixed. It is just that the truss, as if you have thrown into space. Okay. So, if you see that it comes out to be 0, so it is just stiff, it is statically determinate, that you would have learnt when you consider trusses. Let us take 2 other examples. If I look at the middle one, if I again count the number of vertices, here there are 8, and the number of bars there are 12. Okay. Then you get this Maxwell's rule gives 1. Here, as we will discuss a little later in this lecture, it actually turns out to be 2 minus 1, meaning that there are 2 degrees of freedom, 1 state of self stress, 1 over constraint and 2 degrees of freedom. Maybe you can see over constraint already in this portion, because we consider those examples. And you would also see degree of freedom in this loop, that is a 4 bar linkage, and then in this loop, once it is stiff, there is another 4 bar linkage here. So, there are 2 degrees of freedom. Okay. On the other hand, if I go to the third example, turns out to be 0, it has 0 degrees of freedom, 0 states of self stress. So, given a truss, we do not know how to find, even if formula presents a number here, the Maxwell's rule, we do not know how many degrees of freedom are there, how many states of self stress are there, for which we have to have a method. Before that, we have this Maxwell's rule applied to a linkage. Normally, we would use the degrees of freedom formula of Grubler, but here if I do with the Maxwell's rule, we get the same answer, meaning that there is minus 3 and there is minus 3. So, minus 3 whenever degrees of freedom formula given by the groupless formula is negative, that actually means they are over constrained. Okay. That is negative degrees of freedom, which according to this is like 0 minus 3. That means that there are 3 states of self stress. This particular one again is a linkage that you have seen it moving in the first lecture itself. It has clearly a degree of freedom, but the formula, both formulae, the Maxwell's rule as well as groupless formula, predict minus 3 degrees of freedom or 3 over constraints according to state of self stress. Clearly there is no stress here, we are able to move it with 1 degree of freedom. Okay. The reason again is that there is special symmetry in this. It is highly symmetric, meaning there are special geometric conditions that exist in many spatial linkages and our parallelogram linkage and so forth. And when those are there, the formulae that we have seem not so useful. That is true, but when there is arbitrary geometry, the formulae are very useful. When you have special geometry, formulas are not able to predict the degrees of freedom or states of self stress. For that, we need to use group theory using some special symmetric groups. Okay. I think I have to get the ink so that it does not fly. We have to use these symmetric groups, which chemists actually use a lot, the group theory, to look at the molecules which have similar constraints, but of course in a different context altogether. Those conflicts that arise due to the symmetries or special geometric conditions can be done by still going for counting. If you notice, both groupless formula and Maxwell's rule rely on counting. There is no computation, there is only counting. When you count, if you want to stick to that counting method, then you have to go to this group theory and then count the symmetric groups that exist in a particular geometric entity, such as a truss or a linkage or a compliant mechanism or whatever. But that requires entirely different tools of mathematics, but if we stick to engineering mathematics, there is a way out of that, which is what we will discuss now. Again, if you were to do this Maxwell's rule, I would recommend that you try, and you would see that Maxwell's rule also does not work. Okay. Now, let us go to just understand this Maxwell's rule before we move on to a technique with which we can identify degrees of freedom and states of self stress even when there are these special geometric conditions or symmetries. A computational technique that gives you rather than merely counting. So, before that, let us understand Maxwell. How does it come about? It comes about because this, whenever you have, let us say I take a truss such as this, and there are some forces acting, and there could also be the ground reactions as we call. Let us say this one has a pin joint to the ground, let us say third link is fixed. So, we have that, and if it is sliding, there will be only vertical reactions, we can freely slide in this direction, what we call simply supported condition. If you put that and draw the free body diagram for this truss, for each vertex, at each vertex there will be the bar forces. Okay, let us say we assume that all bars are in tension. Let us call this is F1, and hence it is F1, F2, F2, F3, F3, and those will come on to these vertices also in opposite directions at this vertex, and I have this ground reactions. I can write two equations of equilibrium at each of the vertices. That is why we have 2V, which is the number of equations. What are the unknowns? Unknowns are each bar has one internal force, that is, in this example it is F1, F2 and F3. If it is statically determinate, in which case this becomes 0, this minus 3 should be here, because that is also the unknown, that is reaction forces. We have, I can call this Rx, Ry, and then there is another one for not this one over here. So, if I call this Rx, Ry, and let us say R2x or something, if I call this R1x and R1y. So, there are 3 reactions for static determinacy, that is where we have this 3 coming. So, basically we are counting the number of equations and number of unknowns. When that is equal, the bar is just stiff, satisfies Maxwell's rule. The same thing applies in 3 dimensions, where you have 3v minus 6 minus b equal to 0. That is the 3D version of Maxwell's rule. At each vertex you can write 3 equations, fx, fy, fz equilibrium, and the number of bars remains the same, and then 6 unknowns, because in order to make a 3 dimensional truss just stiff, we have to have 6 reactions, okay? And that is how the Maxwell's rule comes. Now, let us understand a computational method for identifying special geometries as well, and for that, whatever I just wrote there, if I have a truss, I want to write the equilibrium equation at each vertex. Let us say I take this vertex, let us say there are ground reactions like that, meaning that our truss is fixed here, whereas here it is pinned and can slide, whereas this is just a pin. If I have such a thing, these are 3 reactions I have. If I take each bar, let us say I take I separate out each bar like that, okay. Let us show the reaction in the bars, what I just called F1, F2, F3, assuming that all are in tension, okay. So, this is F1, F2, F2, F3, F3, and let us show on the vertex now, this vertex, okay. We already have these forces, so let me show them in that color. Okay, so here we have that force and this force at this vertex, and then the forces due to the bars also act on that in the opposite direction. If it is like that, it will be like this, it will be like this. Okay. Now, let us equilibrate this vertex, okay. The vertex that we have, let us write equilibrium equation for that. Let me give some symbols for these, calling this R1x, this is R1y, and then F1, F2 we have. I can write an equation in the x direction, R1x, in the positive if I take my x axis like this and y axis like that, that will be R1x, and then I will have F1 if I take this angle to be, let us say theta 1, I can write this as F1, I am looking at this force now, F1 cosine theta 1, and then I have also F3 plus F3, I am looking at that one now, that should be equal to 0, right. Similarly, I can write in the y direction, I have R1 y, and I will have F1 sin theta 1, the vertical component of our F1 at that vertex, and then I do not have anything else, equal to 0. Those are the 2 things in vertical direction. Similarly, I can write for this vertex and that vertex, I get one more equation, one more equation, one more, 4 more equations, right. They can be put into the form of a matrix, which is what is shown here. What it means is that what I called this F1, F2 are the bar forces. So, let us say I have F1, F2, F3, there are only 3 bar, that is why size of this is b by 1 is equal to, I can take this F3 and external forces, not F3, this R1x, R1y, all of those are external forces, I can put them here, okay. These are the external forces, which is this F vector. Here whatever entries that we get, that is these equations put into matrix form is this equilibrium matrix. All we are doing is we are getting an equilibrium equations put in the matrix form, so that there are bar forces which are unknowns, forces of the vertices are known to us. Of course, the reactions we do not know, But if we apply the static equilibrium for the whole truss, you can actually calculate these reaction forces for given applied forces on the truss. You know how to do that, right? That is what this equilibrium matrix means. This equilibrium matrix has significance in the sense that when it is not a full rank, it gives you certain thing, as we will discuss later. Before we do that, let us go to something that takes care of displacements and elongations. Again, if I have this 3 bar thing, let us say I move them arbitrarily. So, this goes there, this goes here, this vertex goes there. So, it may become something like that. So, this bar has elongated, this bar has elongated, whereas this bar has contracted. So, there are these elongations. These bar elongations can be compared to or related to vertices displacement. For example, this one has x displacement, y displacement, this has x displacement, y displacement, this has x displacement, y displacement. Let me draw them with a different color. So, you can see x displacement, y displacement, x displacement, y displacement, x displacement, y displacement, the vertices. That is why its size is 2v by n, 2v by 1. So, these can be related using pure trigonometry, linearized, so that you can put in the form of a matrix like this. That is called a compliance matrix. This also has interesting properties that we will understand. And interestingly, these two matrices, the C matrix and H matrix, the compliance equation matrix, equilibrium equation matrix, have a relationship that is shown here, which follows from the principle of virtual work. If you recall, principle of virtual work states that external virtual work is equal to internal virtual work. Okay. And here we have that external virtual work is equal to internal virtual work. This is external virtual work, this is internal virtual work. What does it mean? We imagine virtual displacements delta u, the truss is there, we just imagine, they are not real displacement, they are virtual displacements. Then what is the work done by external forces? F transpose delta u is external virtual work. Internal forces, bar forces are p's, they are multiplied with elongations, which are again virtual elongations because of virtual displacements, that gives internal virtual work. They being equal to each other is the principle of virtual work. And here if you substitute, taking the starting principle of virtual work, for delta E you substitute C delta U, that comes from this relationship. And likewise for F we get H times P, again is F transpose, P transpose, H transpose. If I look at this equation now, you conclude that C is equal to H transpose. So, you can either start with equilibrium matrix or compliance matrix, they both are transpose of each other. You should try this, we have not written this, we just wrote partly this one for a simple truss. If you do that, you will see that it is true, and the proof of course is right here. Okay. Now, why do we care about these? It turns out that the rank deficiency of the C matrix indicates degree of freedom of a truss or a compliant mechanism if it is made of bars, which most compliant mechanisms are. Likewise, rank deficiency of the H matrix indicate the state of self stresses, states of self stress. Okay. And this null space of the C matrix indicates instantaneous rigid body modes, and similarly the null space of this H matrix indicates states of self stress and their modes, meaning if there is a truss and which part of that truss has a degree of freedom and which part of that truss has state of self stress will be indicated by looking at the null space of this rank deficient one. If it is not rank deficient, if it is a full rank, that means that there are no degrees of freedom. When this is a full rank, there are no states of self stress. Okay. Whenever there is rank deficiency, here we should look at the column rank or this in this case 2V, in this case it is B, or what you type in MATLAB rank of a matrix, it usually gives this column rank, and you look at that. If it is not a full value, that means that that particular truss has a degree of freedom, looking at compliance matrix, and the corresponding null space vector or null space vectors, if rank definition is more than 1, gives you the rigid body modes, and likewise for equilibrium matrix we get states of self stress. So, it is best to see that with an example that we already considered, that this one has 2 degrees of freedom and 1 state of self stress. So, if I construct this C matrix, you will find that it is rank deficient by 2, and that is exactly what we have here, 2 degrees of freedom. If you look at H matrix for this truss, you will find that it has rank deficiency of 1, which is exactly what we have here. So, if I look at the null space modes of this matrix, I get this. So, here in one case this part is simply moving, that is 1 degree of freedom that we already said, there is 1 degree of freedom for this portion, there is another degree of freedom here which we see over there. So, this is moving like a 4 bar, and this part is moving more like a rigid body, because that is what it is. And if you were to look at the modes, null space modes of this H matrix now, you will also find how the stress is distributed among these elements. Just like this gives motion, null space vectors of H matrix give you the state of self stress. Looking at one way, this physical example of trusses using this compliance matrix and this equilibrium matrix, you actually understand the null space and other linear algebra concepts from a physical perspective. And you should review some of the linear algebra if you do not understand what null space means for these matrices. But important thing is that by doing little bit of computation, we are able to actually get the degrees of freedom and state of self stress split from the Maxwell's rule. And we can also use stiffness matrix, which is from the finite element framework. Here we have the compliance matrix relating displacements and bar elongations, equilibrium matrix relating bar forces and forces acting on the vertex, external force. But what we want is actually the stiffness matrix. Okay. So, let me erase this little thing. What we want is a stiffness matrix which is going to relate, stiffness matrix K relates vertex displacements to forces on the vertices, Ku equal to F, like Kx equal to F, like a spring equation. And that comes out here, because for that we need additional relationship which can be thought of as constitutive relationship, constitutive relation. What this is saying is that how our bar forces, internal bar forces are related to elongations. That will be a function of cross section properties as well as material properties which are contained in D. For a bar, we know this AE by L, which is the stiffness or spring constant of the bar, which is what this is, the bar force versus its elongation. If you define that, then we can get this stiffness matrix. We start P equal to dE and then substitute for E Cu, and then we have the H into P, P we have now that H into P comes from this equation, H into P that we have here. Now, if you look at this again, you try to substitute for this HP that we have now, which is from this equation, it is just force itself, force vector. So, what we have here in this thing, okay, what we have there is our stiffness matrix. So, by having this constitutive relationship, the D, we get HDC or C transpose DC or HDC are equal to HD H transpose, because we already discussed that C and H are related by transpose. This is what we have in the finite element framework where we normally use the letter B to relate strains and displacement. Instead of C we use a B, it will be B transpose dB. D is basically stress strain relationship there. That is what we have in this framework for the trusses. If you look at the stiffness matrix, its rank deficiency indicates rigid body modes again. That means that the structure is not stiff. There may be over constraint which it will not be able to tell you, but if there is a rank deficiency, then it tells you that it has a degree of freedom. That means the thing is not properly constrained, which has like Grubler's formula like degree of freedom. Okay. That is a stiffness matrix can also be used. If you compute it using finite element framework for a truss, that also will give you the degrees of freedom, but not state of self stress. For that we have to construct the equilibrium matrix H and look at the rank deficiency of that matrix. Just to conclude this lecture, we have a few points to note that Maxwell's rule and Grubler's formula are equivalent. When one fails, the other one also fails. Both work by counting. Counting in the case of Maxwell's rules, number of vertices and number of bars. Grubler's formula, number of bodies, which is the number of bars, but also the joints and the type of joints and so forth. That will not tell you whether there are any self stresses or degrees of freedom. It only tells you the total number or DOF minus SOSS. But if you look at the compliance matrix and equilibrium matrix, their rank deficiency not only tells you the degrees of freedom state of self stress, but one thing to note is that this computational method also tells you only instantaneous, meaning in that particular configuration what are the degrees of freedom, which sometimes are called infinitesimal modes. That is all it will tell you, but not over a finite range, because we have linearized the equations over there. Degrees of freedom and state of self stress come from rank deficiency of respectively compliance matrix, equilibrium matrix, but they are only instantaneous. But if you want in the finite element framework stiffness matrix, that can be used, or rather its rank deficiency gives you instantaneous or infinitesimal degrees of freedom in that configuration. If you change the configuration, you have to redo the rank of the stiffness matrix and find if that is rank deficient or full rank. Okay. There are some linkages or trusses whose rank will change from configuration to configuration. They are called metamorphic mechanisms or metamorphic trusses. So, their infinitesimal modes can be found in any configuration by doing this rank analysis. So, we have discussed the counting method, which fails if there are special conditions, and a computational method, these two, where we can find instantaneous or infinitesimal degrees of freedom or states of self stress. And this mobility analysis is crucial to design of compliant mechanisms. It will not guide you to design something, but after you design you can analyze it to see if it is properly constrained or not. We will see some examples later on in the course. Thank you.